In the last lesson, we explored functions like f of x equals x squared plus 2x. And what we were doing was finding the derivative function, okay, or the gradient function. And remember, the way we got the gradient function, f dash x equals, is we had the limit as h approaches 0. We were choosing a y value here, f of x plus h, take away the other y value over x plus h, take away x, which was just h. That's the first principles formula. So we ran it through, it took 7, 8 lines, depending on what it was like, and we would have got, in the end, f of x, or f dash x rather, equals 2x plus 2 after doing first principles. So remember what that thing does, that's our gradient function, and it says, hey, give me a value of x, and I will tell you the instantaneous rate of change at that point. So if remember I did f dash 2, that's going to be 2 times 2, which is 4, 4 plus 2 is 6. So the instantaneous rate of change, the gradient of the tangent at x is equal to 2 is 6. That's what the derivative does. Right, so it's pretty cool. I mean, telling you, working out the instantaneous rate of change at any given point is pretty good. It's pretty handy to know that, but it's a lot of work. Remember how much work went into this last example? Expansion of the cubic, the perfect cube, etc., etc. So what if I told you there's a method to obtain the derivative in one line? Here it is. If f of x equals x to the n, f dash x equals n x n to the power of n take 1, where n is 1, 2, 3, i.e. a positive or an element of z positive. All right, the process of finding the derivative function is called differentiation. So the process that we go through to take this to this is called differentiation. And in 1-2 methods, we'll only derive single terms. The derivative does not work on something like this, okay, that we've got something all to a power. And to derive this, you must expand first and then derive, although we do these in 3-4 methods. All right, so let's find the derivative of this expression here. So first of all, I'm going to let f of x equal x to the 5 take away 2x cubed plus 2. All right, and why did I do this? So that I can use some function notation to describe my derivative. I'm going to say f dash x equals. Now, if you want to use first principles, you can. But remember, that's going to involve working out what f of x plus h is, which is going to involve you putting x plus h, then raising it to the power of 5. That's terrible. Okay, and it still gets even worse because I'd have to do x plus h to the 3 plus 2, and then I'd have to subtract it from that. So it's going to be a nightmare. So we're going to use this rule here. So I'll try to talk you through it, okay, and see if you can follow it. It's fairly simple once you actually have done it a few times, but the first time it's going to seem weird. Right, so what you do is you grab the power and you multiply the coefficient by the power. So at this stage here, it's going to be 5 lots of 1. So we're going to say that that's 5. You write your pronumeral down there, which is going to be x, and you decrease the power of this by 1. So it goes down to a power 4. Right, so that's the first term differentiated. Okay, and that's what this rule describes here. It basically says, hey, to get to the derivative function, grab that n and multiply whatever is out the front by that n value. So that becomes n, and then you drop the n power, or the degree of the power, down by 1. Right, so this one here, what we've got is 3 lots of -2, which is -6, x, and 3 goes down to 2. All right, this constant term here, the way to think about the constant term, I suppose, is that it's going to get dropped. Okay, that constant term is going to get dropped. Now, what is it? Well, or why does it get dropped? Well, what we've got here is 2x to the power of 0, if you want to imagine it like that. All right, where x to the 0 is 1, 2 times 1 is 2. 0 multiplied by 2 will give us 0. 0 multiplied by this gives us 0. So anytime you see a constant term, we can drop it in the derivative, okay? And that there is our derivative, or our gradient function, okay? And again, it's based on this. That's why we call it the derivative, okay? Because it's derived from the original function that does something totally different, okay? It gives us gradients of tangents. This one gives us y values. So again, it's important to note the difference between the two functions. All right, so that's our first ever derivative by rule here, girls. So that's an exciting time. Those of you who continue on to 3-4 methods will just do truckloads of these. All right, find the derivative of this and thus find f dash 1. So again, it's important to know what this is basically saying is, hey, you've got this function. Can you find me the derivative and then can you tell me the gradient of the tangent at x is equal to 1? That's in English what this is basically saying. Sure, I can. F dash x equals 3 multiplied by 3 is equal to 9. X, reduce the power. 2 multiplied by negative 6 is negative 12. X, reduce the power, that's a power 1 or just 1. Constant chops out, so we're left with that. So there's f dash x for first mark. Then we're going to do f dash 1. That means basically bang x equals 1 into the derivative function. That's 9, 1 squared, take away 12 times 1. That's going to be 9 take away 12 equals negative 3. So the gradient of the tangent at this particular point on the function at x equals 1 is negative 3. And again, that tells us that at that point the function is going, as x increases, the y values are going down. Right, so a bit about modern calculus was independently developed by Newton and Leibniz, though at the time Newton accused Leibniz of plagiarism. Nothing like a little catfight between mathematicians, but it actually turned out quite sad for Leibniz. Much of the notation used in calculus and even the name calculus itself was developed by Leibniz, okay, the German. And Newton's name, he gave it the name the science of fluents and fluxions. It just was not quite as catchy. So we do use much of Leibniz's notation and the name. But Leibniz was accused of plagiarism, and it was interesting to note that on the panel that heard his case, it was chaired by none other than Newton himself. Okay, so the person who found that Leibniz was guilty of plagiarism was in fact Newton, the person who accused him of plagiarism. But tough to win a case when that's the way it's going to be dealt with. Newton himself apparently was not the nicest of blokes, but geez, he was a smart bloke. And yeah, so calculus was his great life's work. I know he's got the object motion laws, which are used with calculus, but yeah. So it's an interesting story if you want to see the background of calculus. All this happened, I think, in about the 1600s. So it was quite some time ago. So finding the instantaneous rate of change uses a small change in y values with respect to a small change in x values. So that's what we're doing basically, is to find the instantaneous rate of change. We have a small change in y with respect to a small change in x. And in Leibniz, he used the Greek letter d to represent change. Thus, when you see this in terms of calculus, dy dx, it means small change in y divided by small change in x, or the instantaneous rate of change. And that dy dx is another way of saying f dash x. Okay, so we say dy dx. All right. Now, never, I repeat, never cancel out the d's. It's meant to be kind of a label for the derivative. Okay, so dy dx. Okay, we don't want to see those d's cancel out to give us y over x. Okay, it's a label. It's basically the same as f dash x. Okay, and I've had this graphic in my notes for some years now, and no student of mine has ever done this on a paper. So I'm going to keep this bloke in, okay, because I'm hoping that you see this and go, oh yeah, no, d's can't cancel out. All right, so if x is equal to t to the power of 3 plus t, find dx dt. Find a small change in x with respect to a small change in t. All right, so what that's basically doing is find the gradient function for me, except it wants us to use what we call Leibniz notation. And that's okay. All right, so we can do the same thing. We're going to say dx dt is equal to 3 times 1, which is 3, t, reduce that power down to 2. All right, what do I do with t itself? Well, t is being raised to the 1. 1 times 1 is 1. T to the 0, okay, t to the 0 is 1. So t becomes 1. So there's my derivative function using an alternative notation. That's called using Leibniz notation. All right, now I personally like function notation better. This just looks cleaner. All right, so if f of x equals x squared, f dash x is equal to 2x. And it's just much easier to use. But note that all the formulas on the Methods 3-4 formula sheet are all written with Leibniz notation. So you need to have a firm grasp on it, and you need to be able to use it. All right, now if our function is z equals this, find the z dt. Okay, so we want to find the derivative function. Now, I'm going to hold off finding the z dt in one step on this, because remember what I said about scenarios like this. We can't actually differentiate things with brackets. Okay, it doesn't work the same way as it does with single terms. So what I'm going to do is say that z is equal to, and I'm going to expand this out to make it single terms. I'm going to go t plus 2, 2t, that's going to be 4t squared. Take away 4t plus 1. All right, so that's the perfect square expansion of that. All right, now I'm going to go z equals, and I've got 4t cubed, take away 4t squared, plus t, plus 8t squared, take away 8t plus 2. All right, let's collect them up. 4t to the 3 plus 4t squared, take 7t plus 2. So there is another way of writing z. Z is this, z is also this. Now we've got it to single term, we actually can get our derivative function. So we're going to say dz dt is equal to, and then just run our derivative by rule process. So 3 times 4 is 12. T, power goes down by 1 from 3 to 2. That's going to be 2 lots of 4 is 8. T, take away, so t to the 1, or just t. That's t to the 1. 1 times negative 7 is negative 7. T to the 0, t to the 0 is 1. Constant chops out. There is our derivative function. All right, might be an opportune time on the calculator to show you what happens there. So a couple of ways of doing it. I like to define functions. Define f of x equals, what's my function? 2x take 1 all squared x plus 2. All right, so I'm going to expand it. So expand f of x, which gets it down to single terms. And then what I can use, girls, is a function called diff, calculation diff. And what you do, you feed diff an expression or a function, and it'll differentiate it for you. So this is the expression I want to differentiate. And the way I can do that quickly is go shift exe, and that will shift, or that'll say, hey, differentiate whatever's in the answer slot, ANS, and the answer slot is the slot prior to this. So it's going to differentiate this thing here. Okay, and it is 12x squared plus 8x takes 7, or in our case, we got it using the rule and did it by hand. 12t squared plus 8t takes 7. All right, so that's one way of doing it. The other way of doing it is to use the template in Math2. So Math2 is this, which is d dx. All right, so you hit the independent variable that you're differentiating for, throw in what you want it to differentiate, and it will do it like so as well. So that's another way to get it. All right, what about this one here? If y equals this, find the derivative. All right, well, we only differentiate single terms. This is all being divided by x. But what we're going to do is expand it. So x squared over x plus 3x over x. Those x's cancel out, leaving us with y equals x plus 3. Now let's differentiate by saying dy dx equals, x is currently to the power of 1. 1 times 1 is 1. X to the 0 is 1. So the derivative in this case is 1. The final type of notation, girls, is called operator notation, and it's my least preferred method, and I don't see it that often, but we do need to cover it just in case it's something that comes up. So often a question says to find the derivative of that with respect to x. This can be written as find d dx of this expression. So it's called operator notation because it's only dealing with expressions. So this basically is d dx of this expression here. So we're going to go 3 times 6, which is 18, z to the 2. Take away 2 times 4 is 8, z to the 1, or just z. Okay, so there is my derivative expression, okay, or the derivative of this expression here. All right, and lucky last, find when y equals 4 take x cubed has a gradient of -6. So on the function itself, this is basically what we're doing. I'm going to swing in a GeoGebra page here to show you what we're actually doing. Okay, so our function is f of x equals 4 take x cubed. There it is there. And what we want to know is, when does it have a gradient of -6? Okay, so when along the line, exactly along the line, will it equal -6? Here's where calculus really hits its stride, girls. So calculus is going to be so strong here. All right, so what we're going to do is get a gradient function. I'm going to show why it's important to be flexible here. I'm going to say let f of x equal y equals 4 take x cubed. And I'm going to find the derivative function, f dash x equals. Now, 4 is x to the 0. 0 multiplied by 4 is 0. That term chops out, so that's going to be 0. 3 multiplied by -1 is -3x squared. All right, and we want to know when it has a gradient of -6, i.e. when is the gradient function, when is f dash x going to equal -6? That's what it's asking. When is f dash x equal to -6? All right, so basically what I'll do is I'll replace f dash x with -6, and here we go. Divide by -3, divide by -3. And that's going to be 2 equals x squared. X is equal to plus or minus √2. Okay, so this seems to be suggesting that when x is equal to √2 and negative √2, there's going to be a gradient of -6. Okay, so it's saying, hey, basically we've got 2 spots where that happens. All right, so let's find out, in fact, whether that is the case. So the first thing I will do is I'm going to do f of square root 2. Okay, and I'm going to plot that point there. So square root 2 comma a. Oops, why isn't it letting me do that? Square root 2 comma a. Unbalanced. Okay, so there's one of the points. Okay, at that. Now let's do the other one. So f of, in fact, we know what that point's going to be. It's going to be negative square root 2 comma a as well. No, it's not going to be that. There it is there. All right, so I'm going to get this program to draw a tangent. So what you do, how do you use it? Select a line, a point or line. So select the line and the point. So there is its function there. Notice that it comes up with the gradient or the linear function, which has a gradient of -6, surprise, surprise. Now what should happen if this is correct is this line should run parallel to this line here, the one that's drawn here, because it's saying basically at plus or minus √2, when x is equal to plus or minus √2, this function is going to have a gradient of -6. So let's draw our second gradient there. Oh, come on. U and U. No, U. This is not going well. Come on, gradient. Tangents. Select point. Select line. Select point. Why isn't this working? I just paused the video to sort it out and it did it first time. So I don't know what was going on. Anyway, what we can see is these two lines are parallel. You can also see the equation of this second line here, which has a value of -6 sitting in the M spot. So yeah, that's the reason why we get two solutions there, is there's 2 points where the gradient is equal to -6. All right, so it's your turn now, girls. So 17B, questions 1 to 13 are all going to involve using derivative by rule.